How does an alternator work generally? An alternator is an electrical device that generates alternating current, AC, electricity. It's commonly used in vehicles to charge the battery and power the electrical systems while the engine is running. Here's how an alternator works. The rotor of an alternator is a critical component responsible for generating the magnetic field necessary for the generation of electricity through electromagnetic induction. It is typically a cylindrical or disc-shaped piece located within the alternator housing. The rotor can be of two main types. Squirrel cage rotor. This type of rotor consists of a series of metal bars, often made of aluminum or copper, that are arranged in a cylindrical shape and connected by shorting rings at both ends. These metal bars are parallel to the axis of rotation. When current flows through the bars, it generates a magnetic field around the rotor. As the rotor spins due to the engine's mechanical power, the magnetic field also rotates, which induces an alternating current in the stator coils. Wound rotor. In this design, the rotor consists of coils of wire wound around an iron core. The winding of the rotor is similar to that of the stator coils. The rotor windings are connected to external circuitry through slip rings, allowing electrical connections while allowing the rotor to rotate. The current flowing through the rotor windings creates a magnetic field, and as the rotor turns, this magnetic field induces voltage in the stator coils. In both cases, the key principle is to create a rotating magnetic field within the alternator's stator. This rotating magnetic field induces an alternating current in the stator coils according to Faraday's law of electromagnetic induction. This AC output is then rectified and regulated to produce usable electrical power for charging the battery and powering the vehicle's electrical systems. In summary, the rotor in an alternator is the component that generates the magnetic field, which is essential for the process of electromagnetic induction, leading to the generation of alternating current electricity. Let's delve into the concept of the stator in more detail. The stator is another crucial component within an alternator, working in conjunction with the rotor to generate electricity through electromagnetic induction. The stator is stationary and surrounds the rotor. It consists of a set of coils that are evenly spaced around the inner circumference of the alternator housing. The stator is responsible for receiving the magnetic field generated by the rotor and converting it into electrical current. Key points about the stator. Coil arrangement. The stator typically has three sets of coils, each set spaced 120 degrees apart. This arrangement is often referred to as a three-phase system. The coils are wound with insulated wire and are connected to form a star or delta configuration, depending on the design. Electromagnetic induction. As the rotor's magnetic field rotates within the stator, it cuts across the stator's coils. According to Faraday's law of electromagnetic induction, a changing magnetic field induces an electric current in a nearby conductor. In this case, as the magnetic field of the rotor rotates, it induces an alternating current, AC, in the stator coils. Three-phase AC. Due to the arrangement of the coils in a three-phase configuration, the output of the stator is three separate AC currents, each with a phase difference of 120 degrees. These three AC currents are collectively referred to as three-phase AC. This type of AC power distribution is more efficient and stable for many applications. Voltage generation. The amplitude of the induced AC voltage depends on factors such as the strength of the magnetic field generated by the rotor, the speed of rotation, and the number of turns in the stator coils. The voltage output from each of the stator's three coils is an AC waveform. Rectification and regulation. The AC output from the stator coils needs to be converted into direct current, DC, and regulated to a consistent voltage level. This is achieved through the use of rectifiers and a voltage regulator, as explained in the previous response. In summary, the stator is the stationary component of an alternator that consists of coils arranged to receive the rotating magnetic field generated by the rotor. This interaction between the rotor's magnetic field and the stator's coils results in the induction of three-phase alternating current, AC, electricity, which is then converted, rectified, and regulated for charging the battery and powering the vehicle's electrical systems. The magnetic field is a fundamental concept in electromagnetism, and it plays a crucial role in the operation of alternators and many other electrical devices. Here's an explanation of the magnetic field and its significance in the context of an alternator. Magnetic field. A magnetic field is an area in which a magnetic force is exerted. It is created by moving electric charges, such as electrons, in a current-carrying wire. Whenever electric charges are in motion, they generate a magnetic field perpendicular to their motion. In the context of an alternator. Rotor's magnetic field. The rotor of an alternator is designed to generate a magnetic field when an electric current flows through its coils. This magnetic field is generated due to the motion of electric charges, current, within the rotor's windings. The strength of the magnetic field is directly proportional to the current flowing through the rotor coils. Stator's role. The stator's coils are placed around the rotor, so when the rotor's magnetic field rotates due to the engine's mechanical power, it cuts across the stator's coils. This changing magnetic field induces an electric current in the stator coils, as described by Faraday's law of electromagnetic induction. The induced current in the stator coils is what generates the alternating current, AC, electricity. AC generation. The alternating current generated in the stator is a result of the rotor's rotating magnetic field. As the rotor turns, the magnetic field changes direction, which leads to the continuous production of AC in the stator coils. The specific design of the rotor and stator, as well as their relative movement, ensures the production of a consistent and usable AC output. In summary, the magnetic field is an essential component in the operation of an alternator. The rotor generates a rotating magnetic field through the movement of electric charges, and this changing magnetic field induces alternating current in the stator coils. This induced current is the basis for generating electrical power that can be used to charge the battery and power various electrical systems in vehicles and other applications. Induced voltage is a phenomenon that occurs when a changing magnetic field interacts with a conductor, resulting in the generation of an electromotive force, EMF, or voltage across the conductor. This process is governed by Faraday's law of electromagnetic induction and is a fundamental concept in electromagnetism. In the context of alternators, induced voltage is a key factor in generating electrical power. Here's an explanation of induced voltage in the context of alternators. Changing magnetic field. When a magnetic field changes in strength or direction, it causes lines of magnetic flux to move. This change in the magnetic field induces a voltage in any nearby conductor, such as a wire. Faraday's law of electromagnetic induction states that the magnitude of the induced EMF, voltage, is directly proportional to the rate of change of magnetic flux through a circuit. Mathematically, this is expressed as induced EMF equals N * delta phi / delta t, where induced EMF is the electromotive force, voltage, induced in the circuit. N is the number of turns in the coil or conductor. Delta phi is the change in magnetic flux through the circuit. Delta t is the change in time. Induced voltage in alternators. In an alternator, the rotor's magnetic field changes continuously as it rotates. This changing magnetic field cuts across the stator's coils, which are stationary. As a result, an EMF is induced in the stator coils, causing an alternating current, AC, to flow through the circuit. The induced voltage in the stator coils is directly related to the rate of change of the rotor's magnetic field. Three-phase induction. Due to the three-phase configuration of the stator coils, the induced voltage consists of three separate AC voltages, each phase shifted by 120 degrees. This three-phase AC output is characteristic of alternators and is used for efficient power generation and distribution. Voltage regulation. The magnitude of the induced voltage depends on various factors, including the strength of the rotor's magnetic field, the speed of rotation, and the number of turns in the stator coils. The alternator's voltage regulator adjusts the field current supplied to the rotor to control the strength of the magnetic field, thereby regulating the magnitude of the induced voltage and ensuring a stable output. In summary, induced voltage is the result of a changing magnetic field interacting with a conductor, leading to the generation of an electromotive force, voltage, according to Faraday's law of electromagnetic induction. In alternators, the rotating magnetic field generated by the rotor induces voltage in the stator coils, producing the alternating current, AC, electricity used to power vehicles and other applications. Rectification is the process of converting alternating current, AC, into direct current, DC, by allowing current to flow in only one direction. This is typically achieved using a device called a rectifier, which is commonly used in electrical circuits to change the polarity of the current and convert it from alternating to unidirectional. In the context of alternators, AC output from stator. The stator of an alternator generates alternating current, AC, due to the changing magnetic field induced by the rotating rotor. This AC output consists of sinusoidal waves that change direction periodically. Need for DC. Many electrical devices, including the majority of vehicle systems and batteries, require direct current, DC, to function. Since the AC output of the alternator is not suitable for these applications, it needs to be converted into DC. Diode rectifiers. Rectification is accomplished using diodes. Diodes are semiconductor devices that allow current to flow in one direction while blocking it in the opposite direction. They act as one-way valves for electric current. Full-wave rectification. Most alternators use a full-wave rectification process, which involves using 4 diodes arranged in a specific configuration called a bridge rectifier. The bridge rectifier takes the AC input and converts it into a pulsating DC output. During the positive half-cycle of the AC waveform, 2 of the diodes conduct, allowing current to flow in one direction. During the negative half-cycle, the other 2 diodes conduct, allowing current to flow in the opposite direction. This results in a series of positive and negative pulses. Filtering. The pulsating DC output still contains ripples or fluctuations. To achieve smoother DC, a filter, often consisting of capacitors and sometimes inductors, is connected to the output of the rectifier. The filter helps smooth out the waveform by storing and releasing electrical energy, reducing the amplitude of the ripples. Voltage ripple. The quality of rectification affects the amount of voltage ripple in the DC output. Higher quality rectification and filtering result in lower voltage ripple, which is important for providing stable power to sensitive electronic devices. In summary, rectification is the process of converting the alternating current, AC, output of the alternator into direct current, DC, using diodes and a bridge rectifier. This converted DC is then used to charge the vehicle's battery and power its electrical systems, providing a consistent source of power despite the fluctuating nature of the AC output from the stator coils. Voltage regulation refers to the process of maintaining a stable and consistent output voltage from an electrical device, such as an alternator, despite changes in load conditions or other external factors. In the context of alternators, voltage regulation ensures that the output voltage remains within a specified range to provide reliable power to the vehicle's electrical systems and charge the battery. Here's how voltage regulation works in an alternator. Purpose of regulation. The electrical systems in vehicles and other applications often require a specific and stable voltage to operate correctly. Fluctuations in voltage can lead to unreliable operation and potential damage to sensitive electronics. The alternator's voltage regulation system aims to maintain the output voltage at a predetermined level under various conditions. Voltage regulator. The alternator is equipped with a voltage regulator, which is a control device responsible for regulating the strength of the magnetic field produced by the rotor. By adjusting the field current supplied to the rotor, the voltage regulator controls the output voltage of the alternator. Load changes. When the electrical load on the alternator changes, for example, when more devices are turned on in the vehicle, the voltage regulator detects this change. It then adjusts the field current to ensure that the alternator produces enough electrical power to meet the increased demand while maintaining a stable output voltage. Battery charging. Another important aspect of voltage regulation is battery charging. The voltage regulator monitors the state of charge of the battery and adjusts the alternator's output voltage accordingly. When the battery is low on charge, the regulator increases the field current to produce a higher charging voltage. As the battery becomes fully charged, the regulator reduces the field current to avoid overcharging. Over-voltage protection. Voltage regulators also incorporate over-voltage protection mechanisms. If the alternator's output voltage exceeds a certain threshold, the regulator will reduce the field current to lower the output voltage, preventing potential damage to the vehicle's electrical systems due to excessive voltage. Under-voltage protection. Similarly, voltage regulators can also provide under-voltage protection. If the alternator's output voltage drops too low due to a malfunction or other reasons, the regulator can increase the field current to boost the output voltage back to a safe level. In summary, voltage regulation in an alternator is managed by a voltage regulator that adjusts the field current to maintain a consistent and appropriate output voltage. This ensures that the electrical systems receive stable power and the battery is charged optimally, enhancing the overall reliability and performance of the vehicle's electrical components. Charging the battery and powering electrical systems are two key functions of an alternator in a vehicle. Let's explore each of these functions in more detail. Charging the battery. The primary purpose of an alternator in a vehicle is to charge the battery. The battery provides the initial power needed to start the engine, but once the engine is running, the alternator takes over the task of keeping the battery charged. Here's how the alternator charges the battery. The alternator generates electrical power as the engine's mechanical energy is converted into a rotating magnetic field by the rotor. This rotating magnetic field induces alternating current, AC, in the stator coils through electromagnetic induction. The AC output from the stator is then rectified into direct current, DC, using diodes and a rectifier, as explained earlier. The rectified DC is used to charge the battery by replenishing the energy used during engine startup and by compensating for the power consumed by the vehicle's electrical systems. The voltage regulator in the alternator controls the output voltage to ensure that the battery is charged optimally without overcharging, which could damage the battery. Powering electrical systems. In addition to charging the battery, the alternator also provides power to the various electrical systems and accessories in the vehicle. These systems include the lights, radio, air conditioning, power windows, dashboard instrumentation, and more. Here's how the alternator powers these systems. The rectified and regulated DC output from the alternator is distributed to the vehicle's electrical systems and accessories through the vehicle's wiring system. The constant supply of electrical power from the alternator ensures that these systems can operate without relying solely on the battery, which would drain it quickly. As the vehicle's electrical load increases, example, turning on lights or using the air conditioning, the alternator adjusts its output to supply the additional power required. The voltage regulator plays a key role in maintaining a stable output voltage, which is important for the proper operation of sensitive electronic components and systems. In summary, the alternator performs the dual functions of charging the vehicle's battery and powering its electrical systems. It generates electrical power through electromagnetic induction, converts it to direct current through rectification, and regulates the voltage to ensure optimal charging of the battery and reliable operation of the vehicle's electrical components and accessories. In summary, an alternator converts mechanical energy from the engine's rotation into electrical energy by inducing alternating current in the stator coils. This AC is then rectified into direct current, regulated, and used to charge the battery and power the vehicle's electrical systems.